This subtitle is really how I've presented this elsewhere in terms of talking about modern methods for reform scientific inference in health and medical sciences. And I've, as you saw from my brief subtitle, there's the emphasis here on addressing cognitive problems. I think that because these problems are so difficult to address in scientific terms and are uncomfortable to talk about in human and social terms, they've been neglected, tremendously neglected compared to problems that are easier to deal with in a technical fashion, such as confounding and other familiar sources of bias like selection bias and measurement errors. So, and I won't get through most of these slides, but I hope to hammer some key points that we need to learn how to systematically deal with and teach about these biases, as we've done with those others, mechanical biases like confounding. And because they're larger, more pervasive, and socially more important than recognized in current methodologic texts and literature. Now, the behavioral economics and cognitive psychology literature recognize their importance, and social psychology. But they've, of course, focused on literature in social sciences. When I read the medical literature and the health sciences literature, I see the same problems going on, sometimes worse because of all the financial stakes involved. So I'd say their coverage needs to displace many of the finer points of statistical methodology. But what I'll focus on is how statistical methodology is itself a source of cognitive biases. And that's a big problem in our research environment. As some of the earlier speakers, from what I've seen of their titles, prepared very well, is that there's no statistical analysis accounts for all sources of uncertainty about inferential targets, such as causal effects. And this failure to account for sources of uncertainty causes overstatement of conclusions. The big problem is that most of statistics education doesn't not only doesn't talk about these problems to a great extent, but it suffers from misinterpretations of already unrealistic statistical results. It focuses on make-believe examples that are perfect experiments and the like. And the resulting mistakes get amplified in discussions and reviews and press coverage. And often motivated reasoning determines the direction of the errors and biases. So I want to give a typical example of what I encounter. I've used this example a lot because it's so perfectly illustrates things I'm talking about. This was a study, and it looked to me like a very well done study in terms of the data collection and so forth. The association between basically SSRIs and autism spectrum disorder, ASD, where it appears, it's difficult to tell for sure, that their initial protocol analysis using the standard Cox proportional hazards model produced a hazard ratio of about 1.6 with confidence interval, what I call compatibility interval, going from about 1.2 to 2.2. But then they implemented an adjustment which is very sensitive to the exact implementation, a more technical adjustment, which gave the same point estimate, 1.6, but now the interval went from 1 to 2.6. But they reported the lower limit down to 3 digits. What they didn't report was that the p-value was 0.0505. And by the way, there's a lot of my colleagues have been against p-values, and I get accused of that, but on the contrary, I'm very much for them because they can reveal things like this. You can see exactly where this fell. And they concluded, as their abstract, the exposure was not associated with the outcome. And this is absurd because you can see the association. Their earlier meta-analysis, they had published a meta-analysis which had a 1.7 for the hazard ratio with a confidence interval or compatibility interval, again, of 1.1 to 2.6. So this new study fell right on top of their earlier results. And yet they reported it as producing no association. Clearly, if we combined all the 4 studies, we would get something that's about 1.6 something for the hazard ratio, with an interval going from above 1 to something around 2.5. So I could go, and might not have time to go into detail about other issues with their presentation of the study, but it's clearly they're trying to spin it as if they didn't find anything. And I see this constantly in reports of medications, medical side effects, and any other product that might raise issues of possible legal liability, which in the United States is a very severe threat. So here's an example of a kind of reform presentation. And what I'd like to encourage here is to say, whenever you read reports, do a translation from what they said into how it really should be said. There's a lot of ways to do that, but this is just one example that doesn't involve much change in terms of any statistics you're already familiar with. So here's a way of putting what they found. The adjustment using Cox regression produced a hazard ratio of 1.59. The p-value was 0.03, which they didn't present for the null, no association. And all the hazard ratios from 1.17 to 2.17 had p greater than 0.05. That's all a compatibility interval means. There's a great exaggeration in the import and meaning of these interval estimates, and like there's some kind of they're capturing genuine uncertainty, but they're not. They're just showing you what had p greater than 0.05 under the model that they're using for adjustment. And then they could have said using instead this particular technique, the association was the same. It was about 1.6. The p was 0.05, but now this interval was wider, so everything from 1 to around 2.6 had p greater than 0.05. And then the proper conclusion would be that in utero exposure was associated with autism spectrum disorder, and to about the same extent as in our earlier meta-analysis. The association may, however, be due to residual confounding or other uncontrolled biases. They did say that, and this is kind of obvious. And there's a lot of controversy in the subject that we could go into about how strong that confounding really is. A lot of conflicting claims, but that's not the point. We can acknowledge that that's a source of uncertainty in interpreting this estimate as an effect size as opposed to simply an association. That's been consistently observed across the literature. There's actually a lot of other studies that have found about the same thing. There is this consistent association, and there are plausible biological mechanisms to think that at least part of it could be causal, which is something they don't discuss. So the problem I like to put somewhat dramatically here is that the statistical presentations are bound by these authorities, these authoritative descriptions that date back to before most everybody here was born. And they're really developed in the course, in the context of doing tightly controlled experiments. And there's a heroic narrative of science that science is this continual progress. Old ideas are challenged and methods are challenged, and they're subjecting them to stringent empirical tests. But the problem is that research statistics, what's actually presented in the literature, is decayed by overemphasizing methodologies for those highly controlled experiments. There has been a lot of progress in developing better methodologies, but the interpretations that people give to the results have not kept pace with that. And then these traditional interpretations are often defended with very academic, mathematical, and philosophical appeals, and while underplaying and sometimes just ignoring the harms to actual research environments and public information. And I consider the example I just gave an example of that kind of harm to information. That report was picked up in the press as a no association, exonerating them, when it did nothing of the sort. And that's a harm to public information. Now, the sad part here is that articles decrying this sort of misinterpretation go back all the way to the very early beginning of modern statistics. There's a quote from Carl Pearson in 1906, where he warns that absence of significance relative to the size of the samples, which eventually became this P greater than 0.05, is too often interpreted by the casual reader as a denial of all differentiation, and this may be disastrous. Then I just gave you an example of exactly what he was warning about, and yet this example came up 110 years later. So this illustrates what I was saying about statistics having ossified into peculiar misinterpretations. And R.A. Fisher warned against this problem. So why does misreporting ambiguous results, and that's what we saw, as null, which I call nullism, or an example of it, continue and even remain enforced by some medical journals? It still is enforced. It may have been JAMA that forced that interpretation on them. And it's enforced despite the information damage that it does. Here is a figure that shows over 1 million z-values from Medline over the course of, that covers my career in research and probably most everybody here. The imputed histogram has over 3/4 of the z-values above zero. But look at that histogram. You stare at that figure. I think, well, a colleague of mine really said the people who continue to promote significance testing and null hypothesis testing should have this figure tattooed on their forehead so they see it in the mirror every day. That the damage that this has done blows out a huge proportion of the literature. Now, I put extra tick marks on this figure, which I took from the article, to show where the minus and plus 1.96 so-called P 0.05 cutoffs are, and also a bigger tick mark to show what would be the imputed center. This to show that there's a bit of a pile up at zero, but also that the pile up at that cutoff point occurs both above and below, more above or greater than the 1.96, but also there is some below, which is an example we saw where people are trying to get just above 0.05 because they don't like the association. And the distinction, here's this, I'm going to skip these other quotes from people warning in 1930, 2001, statisticians warning about this kind of problem, about the abuse of automated decision procedures and non-significant p-values, misinterpreting them. So we could ask, well, why does this sort of nullism, why does it continue as a norm? Well, I offer that it enables an illusion of simplicity where none exists, which I call the religion of parsimony, which forgets how nature is under no obligation to be understandable to you. Nature, and especially when we're dealing with human systems and health issues and so forth, we all should know that it's very complex. It also creates an illusion of learning and knowledge or certainty when your own study information is actually sparse and your results are ambiguous. We just saw an example of that. No association claimed when, in fact, the data are quite ambiguous as to how big the association is, and it could be quite large, 2.5-fold or more increase in risk. And it imposes values and preferences of those who believe in the null or have stakes on the null, as I believe some of those authors did, without revealing those values or stakes. There's no revelation there, but several of the senior authors there are psychologists, psychotherapists that very well may have been prescribing SSRIs to pregnant women or recommending them for pregnant women. Now, this nullism is a cognitive and value bias. It's not a matter of statistics philosophy. This is not a matter of the shop-worn controversy of frequentism versus Bayes or any of those other distractions that academic statistics likes to bog down in. Declarations like there was no association when there was an association, but P is greater than 0.5, or the CI included the null, they are not the fault of the bare bones statistical methods themselves. They're not the fault of p-values, and they are not remedied by Bayesian alternatives, Bayesian significance tests. They are instead the fault of a statistics and science culture that encourages or demands declarations of findings from ambiguous results, which most results are. And this vice is synergized by lower publication prospects for honestly reported ambiguity. You could only imagine how much harder it would be to publish an article that said, we did this study, we did great job, we brought in great data, and unfortunately, we really can't conclude much of anything. That would be the honest way to report a result like that. It's valuable data to have, but it's not conclusive in any sense. But it's much harder to get published and if you would report things in such an honest way. So this reality stands in contrast to this romantic, heroic fantasy science. So the harsh reality is that much of statistics serves commitments of certain social networks toward portrayal of facts and to propaganda to bias inferences and policies in favor of the network's valuations of special interests. So I could go on at great length here, but in view of the time, my limited time, I want to go past the reform slides in this and focus on a few points. That reporting ambiguous statistical results as negative or no association generates enduring misimpressions that studies conflict. That, for example, randomized trials refute observational studies, and that there is a replication crisis in health and medical sciences, like we've seen in the social and psychological sciences. The reality is that when I've looked at claims of conflicting literature in the health sciences, medical literature, we see that most of them are completely wrong. They're just generated by doing things. The studies agree, but the initial studies, which may have been large database studies, got p less than 0.05, but then later smaller, maybe more accurately done studies, but smaller, as RCTs tend to be due to their expense, trials tend to be, get p greater than 0.05, even though the results agree as well as the results of that example agreed with previous studies. It's just that their interval estimates are wider because they're smaller. Here's a typical example of that. From the abstract, they claimed use of statins was not associated with risk of glioma. And the odds ratio in that case was 0.75 with the interval from about 0.5 to 1.2. They said, our findings do not support previous sparse evidence of a possible inverse association. In their discussion, they said, this matched case control study revealed a null association between statin use and risk of glioma. Now let's look at the previous studies, which they cite and clearly in their paper. The previous studies, the two they recite, one had 0.72 for the odds ratio, from going from 0.5 to 1, and the other had 0.76, going from about 0.6 to 1. First of all, these point estimates are practically on top of each other in statistical terms. So these studies are, again, incredibly consistent. And when you combine the three in any manner, simple manner, you get, unsurprisingly, about 0.75 for the ratio, and interval now going from 0.6 to 0.9 with p about 0.002. It's clear that there's an association, And there also that the earlier studies had more data. They were less sparse in terms of their evidence than this current study. So there's several misinterpretations that the authors used to promote their study as if it was a new finding refuting previous studies, when in fact all it was doing was replicating the previous studies. And like I said, most of the time when I look at claims of conflict in the literature, I go back and the original studies and look at them, and I find things like this, that there is no conflict. The problem is that some studies are getting P above 0.05 and some are getting P less than 0.05, which is just as you'd expect from studies whose power is very marginal. And even though study proposals generally claim they're going to get 80% power, surveys of literature show that the studies actually ended up with less than, at best, 50% power, and usually much less. So you're bound to get these P waffling around that magic 0.05 cutoff. So here's an example of a reform presentation for that study. The use of statins was associated with risk of glioma, 0.75, but all odds ratios from 0.48 to 1.17 had P greater than 0.05. That's really all they got from their statistics. They should have reported the results agree closely with previous studies, which reported inverse associations of so forth. When all three studies were combined, and that's what they should have done, it's easy to do. The odds ratio was 0.75, P 0.0016 for no association. The association may, however, be largely or wholly due to residual confounding or other uncontrolled biases. There's this consistent association literature. It could be that statins protect against glioma, or it could just be a spurious association, but it's there over and over again in several studies. And one of the problems here is that there are many ways to analyze and interpret data that fall within what is acceptable to some reviewers. And what you did, you maybe got lucky and was acceptable to the reviewers you got. There are many analysis choices that must be made that are not dictated by universally accepted methods, guidelines, or rules. And where did you set the cutoff? They said that was actually a case where they dichotomized the treatment, and there's no universal guidelines or rules for that, and quite a bit of controversy over that. In fact, if you look closely at the statistics literature. Now, as a result, social experiments in which the same data is given to different teams have resulted in a vast spectrum of results. We find that different research teams come up, given the same data, doing things in the way they think is the best, come up with different answers. Consequently, this is how one ought to think about the analyses you see in the papers. They should be viewed as a part of a vastly incomplete sensitivity analysis. What you see in any paper is maybe one, or in the case of the first example I gave, two ways of analyzing the data. The first way, there was a Cox model, and the second was this new method, which in fact, when you tweak it to current standards, you get a narrow confidence interval that excludes one, by the way, in that example. So you should really be thinking, when you look at the study, along with all the other problems, they analyze things in a particular way. Somebody else who made different choices along the way in the garden of forking paths, as Gelman and Loken called it in 2014, people who branched out to different choices could have gotten different results. And in particular, they could have made P go above 0.05 without even trying intentionally, or go below 0.05. So, and I have a lot of commentary here about the problem being problems with statistics, but any reform that still leads to selective, if you ask what will be the effect of making reforms in statistics, any reform that still leads to selective reporting based on study results will distort the distribution of available results relative to all results. So here we see the consequence of generations of using P less than 0.05 as the criterion for claiming that there's an association, p greater than 0.05 becoming a criterion for claiming there's no association. This dichotomized thinking, this kind of dichotomania has produced this kind of literature. But any kind of criterion for publication that's based on the results of the study as opposed to the quality of the study as it was conducted, its design and its data collection, how things came out in terms of how it was executed. Any use of the outcome itself to choose it for publication or emphasis is going to result in a distortion of the literature. So, we can skip over it. These things about the difference between statistics and scientific inference. I could go on at great length about that. And the resistance to the kind of reforms I'm talking about from statisticians who are defensive about having used their entire careers terms like statistical significance and confidence, even when studies provide nothing close to significance and confidence without huge leaps of faith. And I believe that the statistics profession, to a certain extent, it became a guild selling technical products and services based on dense jargon, notation, and artificial precision, whose assumptions and dangers are poorly understood by most users and consumers in soft sciences. This has a complete parallel with product sales in any other area. But the scientific community is not free of guilt here. They contributed to the degeneration of statistical science. Because, for example, and I certainly encountered this, and students want explicit practice rules for memorization to ensure correct answers. Instructors want ease of grading. Researchers want rules for submitting acceptable reports. And reviewers and editors, overburdened as they are, want to ease reviewing and publication decisions. So they want checklists. They can look and see that they was P less than 0.05 or greater than 0.05 in trying to determine whether they should publish this. And then the prevailing rules became popular and destructive via enforced dichotomies. And dichotomies satisfy human drives for definitive conclusions. And they apply even when the study, the real physical data, and the generator of the data is incapable of forcing such conclusions if critically scrutinized. As we saw in both the examples that I just gave. So in any event, I've got to get back to the slide here. So I can go on about statistics education. As I said, the main problem of p-values will extend to any statistics because they stem from truth-subverting perverse incentives and cognitive biases, not p-values. There are perverse incentives that create cognitive biases, wishful thinking, to see what the incentives dictate. And these biases pervade reports in fields like medicine, where there can be huge liability and profitability elements at stake. And the perceptions are manipulated to see incentives for positive reporting while ignoring incentives for negative reporting. Here's an example: reasoning motivated, in this case by commitment to financial stakes, but motivated reasoning can arise from past teaching and past practice, commitment to that. This is one. If you look at U.S. dairy products, you'll often see this label on natural or organic products, but also many others, where they'll say milk from cows not treated with recombinant bovine hormone. This is RBST. Then they're forced to put, with a big asterisk, no significant difference has been shown between milk derived from cows treated with RBST and those not treated with RBST. They don't want to put this here, but they're forced to do so by the government. Of course, this is an immediate red flag that what are they talking about? No significant difference. Why are they forced to put this on here when all they're doing is stating that the milk came from cows not treated with the hormone? Well, it's because a special interest group forced a statement of fact, uh, this statement in black, to be accompanied by a misleading claim in red to defend the use of hormones. Where did this come from? Well, this label has been around a long time, and my attempt to trace back the source goes back to finding these 8 trials from published in Nature in the last century, which found on average a 19% increase in pus, the somatic cell count, from cows treated with the hormone. And the meta-analytic p-value here is 0.004. Let's look at the plot here of these trials, these 8 trials. They were done in the US and in Europe. And look at that. You can see that the general tendency, they fluctuate around as you expect from statistical variation, but they are fluctuating around something above no increase into a positive increase. So how did they come up with no significant? Well, we can't be absolutely sure, but maybe it's a combination of thinking 19% isn't somehow significant in subject matter sense, and also because as you look across these trials individually, all but most of them have p greater than 0.05. This is a very common mistake in reviews in the literature. They say, well, most studies have not found this effect. And all that comes down to is saying that most studies had p greater than 0.05, which, of course, when you look at them, is usually due to the reasons we saw before, because they were too small. It's commonly said they were underpowered to detect the kind of effect that's present, which in this case isn't dramatic, but it's there. It's around a 20% increase in the pus in the milk. So we have a social problem in that the replication crisis is constantly portrayed as one of perverse incentives to make discoveries by searching out statistical significance, producing publication bias. But that's only one aspect, and it's not the only aspect that anyone concerned with literature, including policymakers, need to consider. One of the things is that some have argued to lower significance thresholds to address this side of the problem, but that only increases publication bias. If a lower significance level had been required, the histogram I showed you before would have had an even bigger hole in it. Any selective publication based on results damages the goals of building complete, unbiased public data repositories, and yet the defense and promotion of significance selection continues unabated. It ignores the perverse incentives to fish out and report negative results, which I call upward p-hacking, selecting or focusing on results that give p greater than 0.05, as we saw in the first example, in which they chose to emphasize one particular analysis result over the other, the one that gave p barely above 0.05. And they misreported an ambiguous result as negative. And this happens when researchers, sponsors, and editors want to dismiss undesirable associations, or when replication failures or other challenges to an association are more publishable than mere replication. That, I think, is what happened in the second example with the glioma. In that case, you had a buildup of a few studies that claimed to find an association, or did see an association, but with p less than 0.05. So now it becomes very publishable to publish a refutation. Just another replication, which is all that study was, found the same thing, presented that way wouldn't have been easily publishable in a prominent journal. But now to claim we've refuted earlier studies, we have refutation of them, that is much more publishable. And again, this is a social psychological problem with the literature. Now, I could go into further detail about the Brown study and the other sources of bias there. The fact that, in fact, they did not mention that there were way more than the studies that they cited. They cited three previous studies that were in their meta-analysis. But at the same time, their meta-analysis was published. There was another meta-analysis published that found 16 cohort studies whose summary hazard ratio was 1.74. You'll recall that their summary of previous studies was 1.7, and their study got 1.6. And they also found 5 case control studies with even larger associations. None of that was mentioned. This meta-analysis wasn't mentioned by them. Of course, we could debate how good all these studies were, but as I said, 16 of them were cohort studies. And you get this, again, a very consistent association when it's made to look like there's some kind of conflict in the literature. Why was there no discussion of this? Well, one reason, most writers at the time were certain this highly replicated association was pure confounding. It was reported in medical newsletters as if they had found no association. This is how that Brown study was reported. Use of antidepressants before and during pregnancy does not cause autism or ADHD, a new research shows. Actually, it wasn't antidepressants, it was SSRIs specifically, which of course are the most commonly used ones, at least in the US. 3 studies demonstrate that antidepressant use in women is likely not responsible for ASD in children and was likely due to confounding factors. If you read these studies carefully, there's no way you could reach this conclusion except through having prejudicial priors. In other words, reaching a foregone conclusion. The results are completely ambiguous. And also, they go against the biologic plausibility, the fact that SSRIs, serotonin is involved in embryonic neurogenesis. So, where were we?
This is Marios.
Are we coming to the end here?
I would like to ask you to speak for the whole night, but it's not possible because we have to keep the program. So if you can start thinking about the end, at least for today.
Yeah. Okay. Yeah. Like I said, I was just going to get through a few of these slides. I think, or I hope, that you are getting the idea that in the Brown example, that there's this dominant social bias. We can see this as if all incentives are to discover rather than refute effects. This meta bias is rampant in the replication crisis literature, which uncritically ignores differences in incentives across topics and authors. And the null bias of null testing ignores that. That Brown example has the appearance of what I can call interval hacking, to increase width by adjusting until the interval finally includes 1, even though the adjustment has the appearance of over adjustment, inflating the interval width without removing any bias. The point is not to argue that the SSRIs cause this autism spectrum disorder. That's a massive topic, but rather to emphasize that spin is the driver through the garden of forking paths, all these analysis choices. Objective statistics are perceived, selective, and reported based on preferred causal stories. And in high-stakes settings, which the Brown study of SSRIs is a very high-stakes setting, political and litigation concerns. There's a big fear that people will start litigating against the manufacturers of the drug. Examples abound throughout the health and medical sciences literature where this happens, what I just illustrated. And that should scare you. Statistical training that pretends otherwise obscures and fosters manipulation. So what I try to do, and what I gave examples of, I wrap up here, is to give you tools to trigger you to spot these problems in what you're reading, even when it looks so good, the study looks excellent, and it's presented very objectively and very cleanly. Be suspicious. I want you to be suspicious, and I want you to rewrite the results in ways that are not dominated by these sorts of biases, to prevent confusion of statistical significance and statistical confidence. Replace them with compatibility interpretations and other methods that I've described in a large number of papers, which are cited in these slides later. And in fact, we should make them available to everybody in the conference. I could send these reprints. They're free to read to everyone. And to prevent confusion of statistical non-significance with practical insignificance, present p-values for interval hypotheses and for multiple alternative hypotheses. These are all old ideas. Some people, sometimes they try to attack me, say I'm trying to introduce new things. And these are all ideas I pulled out of literature going back to the 1930s, 1940s, 1950s, 1960s. They're old ideas that should have been taken up in modern times, but somehow languished. And I'm trying to resurrect them, seeing all the problems their neglect has led to. So in any event, there's all these other tools for causal uncertainties, but I can stop there, given that I think I'm out of my time here, right?
Almost.